Hello everyone. Today I'm going to talk about the transistors, perhaps the most important device of the last century, and that has changed our life in so many ways. So in order to understand how transistors work, so you can do the transistors experiment, we will review some of the electronic properties of these electrons in atoms or charges in atoms, molecules, and semiconducting crystals. We will also talk about free electrons and how these electrons, the electrons behave in semiconductors. And we introduce the concept of the Fermi level. We'll talk about the concept of electron holes, so holes for short, which are positively charged quasi-particles, representing a lack of electron in the valence band. We'll talk about how we can charge semiconductors through extrinsic doping, and you can make them conductive. Then we'll talk about this device, the PN junction diode, which is a unidirectional device that transmits current in only one direction. And finally, I will talk about the bipolar junction transistors, the device we will be working with. All right, so let us get started. So you know that in an atom, the energy levels of electrons in an atom. So for example, if you have a hydrogen-like atom with a proton and an electron here, so the energy levels, they grow following this relationship. Minus k squared divided by n squared. So this is, you can show this by spectroscopic measurements, and you will do this later in the course. And this was explained later on by Niels Bohr. So this is from the Bohr model of the electron. You can derive of the electron in an atom. You can derive this energy relationship, where n is an integer number, so it's 1, 2, 3, and so on and so forth. So here is the lowest energy level for n equal to 1, so this is E1. Here we have E2. And if an electron is here, in the ground state, you can excite the electron to this first excited state if the electron absorbs a photon whose energy, h bar omega, is the difference of energy between these two levels, E2 minus E1. So you can take the electron from the ground state to the excited state. You can take two atoms and you can bring them together and form a molecule. So for example, you have atom 1, and here you have atom 2. So if this is the energy level of atom 1, and this is the energy level of atom 2, so when you bring them together, so the electrons in atom 1 and the electrons in atom 2 will be shared now. So they belong to the entire molecule. In this, you create new energy levels. So we have one energy level with the lowest energy, a lower energy, and here an energy level with a higher energy. So this is for a molecule. So for example, if you have representing an electron pointing up here, the spin of the electron, and here is the other configuration. So you get this type, this lowest energy state would be the bonding state, and the molecule goes to this state, and the anti-bonding state is up here. And then you can take an electron from here to here by absorption of a photon, similar to the atom. Right, you can have many atoms together arranged in a crystal. So I will focus my attention on semiconducting crystals, not with metals, because that's what matters for our experiment. So if you have a semiconducting crystal, let's say a semiconducting crystal where we have many atoms arranged in what you can consider as an infinite array, then now the electrons can be shared among the atoms. So now you can have more energy states. That would be similar to a molecule, where the molecule have more than one atom. So for example, if a molecule has more than one atom, you can get many energy states now, because each state can give rise to new states. So you have, and then you start filling up with electrons here. Down, down. And you fill up with electrons until this final level here. And this final level is called HOMO, which stands for highest occupied molecular orbital. The excited states that are equivalent to the anti-bonding states are up here. So we have many states. In the state with the lowest energy is called LUMO, which stands for lowest unoccupied molecular orbital. And again, you can take one electron from here, from one of these states. So for example, you can take one electron from the HOMO to the LUMO and excite here by absorption of a photon, whose energy is the difference between the energy from the LUMO minus the energy of the HOMO. So the semiconductor crystal then will have a different, a similar, but the difference is in the number of the separation between these states here. So now you have many states whose separation is very small at the higher temperature, at room temperatures. The separation is very small. So we draw many states here, very small separation between them, so that you can consider that they are a continuum of states. So now these will become a continuum of states. So you have this state which is entirely filled with electrons, the valence electrons, and this is called valence band. And so this is the VB, the valence band, and up here, this excited state is called the conduction band, or CD short. So you can take electrons from here to here. So you can take an electron from here and excite to emit a photon whose energy is greater than the energy, the difference between the conduction and the valence band, and then you can take a photon from here to here. So these states in between these two bands is what we call the band gap. So right here we have the band gap. And in the band gap there are no real states. Alright, now we'll discuss how these electrons, the electrons behave in a semiconductor crystal. So you know that a free electron the energy of a free electron is given by the momentum squared divided by 2 times the mass. And the momentum is given by h bar k, where k is the weight vector of the electron. So this becomes h squared with k squared divided by 2m. So you can write something called the dispersion relation, the energy of the electron versus the momentum, and this is a parabola. In a semiconductor crystal where the electron is confined in the lattice, in the crystal lattice, you can no longer use the same relationship. So if you took your solid state physics course or semiconductors course, you can show using many models that this relationship is no longer parabolic. So you have a relationship for the valence band. Oh, let's draw here something for the valence band, VB. So the electrons are here, filling the valence band. And up here you have the conduction band. So the relationship is no longer parabolic of the energy of the electron is a function of the crystal, of the momentum of the lattice. And you can, at least close to the k equal to 0, you can approximate that parabola. So you can use Taylor expansion and show that this is approximately a parabola. So from now on, we will focus our attention around this area here, close to k equal to 0. So in this case, we can rewrite, we will express it both the conduction and the valence band as parabolas. because we are assuming that K is close to 0. And here we fill up with electrons. And each electron occupies only one energy state according to the Pauli exclusion principle, because these are fermions, so you can occupy only one state. So each electron can occupy only one state, and in this case you cannot even conduct electricity, because you cannot change the momentum of the electrons if you apply an electric field, because electrons cannot occupy all the levels. So you cannot move them around. So they are fermions, and one important concept of semiconductors is called the Fermi level. So as electrons are fermions, they follow what is called the Fermi-Dirac statistic, so distribution. So it goes, the probability of finding an electron with energy epsilon is minus epsilon minus mu divided by kBt plus 1. So this is the Fermi Dirac distribution. And you can show that when epsilon is equal to mu is called the chemical potential, Fe, we'll call this EF, representing the Fermi level. This is equal to 1/2. And Kb, as you know, Kb is the Boltzmann constant, of course, but the probability of finding an electron in whose energy is EF is 1/2. And this is called the Fermi level. And so the probability of finding an electron in the Fermi level is 50%. You can show that the Fermi level, in a case of a semiconductor, lies within the band gap in between the conduction and the valence bands. So this is EF, right in the middle. So this is not a real level. The electron cannot occupy that level. But no, it just arises from the Fermi-Dirac distribution. And this is an important discussion of semiconductors, an important concept in semiconductors, because this Fermi level can be shifted, and we will deal with this later when you're talking about all devices. Okay, so if the electron is here in the valence band, the electrons are all in the valence band, and the valence band is completely filled, you cannot conduct electricity in this case. To conduct electricity, you have to excite an electron to the conduction band. So for example, by absorption of a photon, you can take one electron from the valence band to the conduction band. By the way, this level here, the zero is arbitrary. You're only interested in differences in energy. So if you come with a photon, here you can excite from here, from the valence band to the conduction band. And now this electron is free to change the momentum, to move around. In some in experimental observations, you can show that you can observe that the electron, after it leaves the valence band becomes positively charged. So it creates a positively charged distribution in the valence band. And interestingly, this system now behaves as if there is a charge there, a positive charge there. Now you can move the electrons around here, or you can see, in a way, you can see that you can move this vacancy around. And this lack of an electron is called the hole, a hole. So a hole is a positively charged particle, while the electron is negatively charged. And then you can move the hole around. So the hole can also conduct electricity. So you can also conduct electricity manipulating the valence band. A way to understand how the hole works, the hole is the lack of the electron, is if you think about, for example, cars in a traffic. So for example, cars in traffic, you can think of several cars in a traffic light. So suppose these are cars, and then you have a space between these two cars. And then you can, let me bring the cars here. It will become easier to visualize. So suppose you have the red light here, the red light, and the cars are waiting in traffic. And there is a gap between car 1 and car 2. So the cars are the electrons, and this gap, this lack of a car, is called the holes. Let's call it the holes. We'll represent it as the holes. So you know that the holes, the gap doesn't move. Only the cars move. So if this car comes here, so an electron moves there, the net effect is that the hole, let me draw it another color, the hole is traveling in the opposite direction. So that it's just a representation of the motion of the hole, while the electrons are traveling in the opposite direction. So it's a positively charged particle. So you know that if you have a negatively charged particle here, E, you know that if you apply electric field here, E, the force is equal to QE, which is equal to minus E. So the force goes in the opposite direction, so of the electric field. So the electron will move in the opposite direction. While a hole, which is positively charged, the force will be plus E, and the hole will move along the direction of the electric field, which is the opposite direction of the electron. All right, so now we can move forward. After discussing the concept of electron holes or holes for short, we can talk about doping in semiconductors. How we can put electrons and holes in a semiconductor. Yeah, another way to visualize, for example, the holes, as I use this example of traffic, is if you have water here in a cup, you have water, and suppose there is a bubble here, a small bubble. So if the bubble is moving down, actually, it's not the bubble itself, but the water. You can think of the water as moving up. So the water is it's like the electron, and the bubble is like the hole, it's the lack of water. So while the water moves up, the bubble moves down. Okay, so how we can control or can place charges in a semiconductor? So we can do through what we call doping. So a semiconductor, like for example silicon, I will draw here silicon crystal. I cannot draw in 3 dimensions, so you have to assume that this is a 3-dimensional crystal. So when you dope, I mean this pure crystal is called intrinsic semiconductor. And again, if you look at the band distribution, you will have simply the valence band completely filled with electrons, and the conduction band is empty. In this case, you cannot conduct electricity in this intrinsic semiconductor. I can also represent this by the previous representation. conduction band and the valence band, and I can fill up here the valence band. However, you can control your crystal in order to change the number of electrons you have in the crystal. So you can do, for example, if you look at the periodic table, so I will consult here the periodic table. So the periodic table goes like this. So you have boron, the periodic table of elements. So you have boron, carbon, nitrogen, aluminum, and here you have silicon or crystal, phosphorus, ammonium, and indium, and other elements. So silicon belongs to this group 4A, this is 3A, this is 5A. That means that silicon has four valence electrons. So it bonds with all the 4 silicon atoms. So each electron, each valence electron will connect to another electron. So the silicon atom connects to 4 other atoms. So we have 4 valence electrons, and here we have 3 valence electrons, and here I have 5 valence electrons. So if you look at, for example, if you take a silicon atom and you replace by a boron atom, so an atom, this atom here, you know that the boron has only 3 valence electrons. So if you take these out and now you replace the silicon atom here by a boron atom, so let me draw the entire network here. So it turns out that you change the number of electrons you had here. So before you had 4 electrons, and now you have only 3 electrons. So this silicon atom here is can no longer form a bond, a covalent bond with the boron atom. So there is 1 electron lacking here. So this becomes, and the net effect is that this becomes positively charged compared to this one. So it's lacking 1 electron here compared to this one. So this is called an extrinsic semiconductor. And this is an example of a positively doped or p-doped semiconductor. So you can also replace, instead of replacing by boron, you can also replace it by another element. You can replace by another element from this group here, which has 5 valence electrons. So let's replace it by phosphorus. So now we have silicon, and now we have P, which stands for phosphorus, not for P doped. Silicon, silicon. So in this case, you have 5 valence electrons now in this region, instead of 4 for the original intrinsic semiconductor. So we have an additional electron here. It's not being shared among the other silicon atoms. Now the question is, where is this electron located in the bond structure? So for this n-doped, this is negatively doped semiconductor, where is it located? So you can show that if you look at the band distribution, again, E versus K. So this is completely filled. Here VB, and here has CB. So this phosphorus atom is donating 1 electron to the system. So this is called a donor. So the electron will be here, right here, in the band gap. So this is a donor state. And you can show that this electron will behave just like you can model it by an electron in an atom according to the Bohr model. That means that the donor states, if you zoom in here, you have several states, and they follow the Bohr relationship. So you have several energy levels, and the donor state is very close to the conduction band. So that at room temperature, by thermal excitation, you can take the electron from the donor state to the conduction band of the entire crystal. So this is called the ionization, and this electron will be ionized to the conduction band. Now the semiconductor can conduct electricity. This n-doped semiconductor can conduct electricity. And this will cause the Fermi level to shift closer to the conduction band. So now it's no longer in between right in the middle of the conduction and the valence band, but it's closer now to the conduction band. The same is valid for a p-doped. So this is the case of the n-doped. And for a p-doped, we have a hole. So the boron atom will be now a sector instead of donor. And the hole will be ionized to the valence band. So we have a hole here. This is the positive, this is the negative charge, so this is a positive quasi-particle. And this can move around the valence band. From now on, I will represent this in another way. So the n-doped, I can simply include an electron here, and I know that there are electrons in the valence band. I just know. And for the p-doped, I have a hole here, so I can have more than one hole for the entire crystal. So you have holes in the valence band of the p-doped semiconductor, and you have electrons in the conduction band of the n-doped semiconductor. And now comes the engineering part of using this type of structures. So the first type of device we'll talk about is the p-n junction diode, which is an electronic device made out of a p and an n-doped semiconductor. So if you have, so suppose this is a material where, let me draw it 3D. So where this is a p-doped semiconductor and this is a n-doped semiconductor. And here you have a junction. So if this is a p-doped, you know that there are electrons there are holes in the valence band. So you have this type of configuration. So and the n-doped has electrons in the conduction band. Of course, it has electrons here, but I'm not interested in. I will not draw, for simplicity, I will not draw here. And the Fermi level for the p-doped is closer to the conduction band, and for n-doped, for the p-doped, is close to the valence band. For simplicity, from now on, I can draw the band structure in terms of space. So if I go from here to here in the device, I will be I will represent this by this drawing here. So I will, for simplicity, also get rid of these vertical lines. And now I can see how the charge distribution when I travel across the device. So when you bring these two semiconductors together, the P and the N, what happens is that the Fermi level, when you travel across the structure, will be the same. So they'll share the same Fermi level. The distribution is the same here in the junction. So if the Fermi level is the same and you bring them together, you now can represent this like that. So you have a p doped semiconductor, B, C, and EF. And the conduction band in this second one, so this is the P doped. And the N doped will have, of course, the same Fermi level. And it has electrons. In the excess electrons in the conduction band. So these are called majority carriers. So for the p doped, the majority carriers are holes, and for the n doped, the majority carriers are electrons. So when you bring them together, the Fermi level is the same. And now the energy of the conduction band gradually decreases until you get it matches the energy of the conduction band in the n-doped semiconductor. So this creates a barrier. So there is a barrier here, a potential barrier, whose energy is given by EV, the electric charge multiplied by the potential, the electric potential. So this creates a barrier, and there are no majority carriers around this barrier. So this is called a depletion layer, or depletion zone, because there are no majority carriers there. So an interesting thing of the semiconductors is that in this case, if you have no majority carriers, so let me draw a little bit smaller. So if you have the P and the N doped crystal, we know that here I have holes and here I have electrons. And in this zone here, the depletion zone, there are no majority carriers. That means that the core atoms, if the holes have moved this way, this region will become negatively charged. The core atoms are negatively charged. And if the electrons move this way, this region will become positively charged. So there is a built-in electric field in this depletion zone. All right, now we can inject charges in this device in order to be able to control charges in this device called the PN junction diode. So this is the PN junction diode. So now, suppose I take this device, let me draw here, very small, a very small device. And now let's apply a voltage across this device. So apply a voltage here, a bias, a voltage across this device. What happens to the bond structure when I apply this voltage? So in this case, I will be controlling their Fermi level. I will be injecting charges and also shifting the Fermi level. So the Fermi level will no longer be the same. So if you apply in this configuration, this is called a forward bias. Then the P doped side here, then doped, then the Fermi level was shifted here, and the energy of the conduction band was shifted as well. So now this potential barrier now is smaller, and the electrons can travel or can flow from the N doped to the P doped side, and you can establish a current. So we represent here the potential you are applying, and as the current is by convention, it's like the motion of positive charges, so the current will be the opposite way to establish a current this way. So if you look at the voltage, at the current of this device, current I versus voltage, in the forward bias configuration, the current grows, potential electric grows exponentially. Now suppose you reverse this voltage. So what happens to the band distribution? Or to its energy levels. So if you reverse the voltage, so let me suppose now it's minus here and plus here. then this will be better up here. Then this depletion layer here, this potential barrier, will increase so that you cannot move electrons from here to here. Well, the holes cannot move this way either. While in this case, in the forward bias configuration, the charges can flow from one side to the other. Now the potential barrier is too high now, so that the electrons cannot go from one side of the junction to the other side. And this is called reverse bias. There's still a very small current, close to zero, some drift current, but this device transmits charges only in one direction, in the forward bias configuration. So this is the PN junction diode. So this side is the reverse bias. And you can represent this by this symbol. So the PN junction diode has this symbol, and if you apply here this here plus, here minus, the charges can only flow this way in the forward configuration. So if you're trying to apply a reverse bias, here plus, here minus, so the current will not be able to flow in this direction. So there's a stop here. So it's a unidirectional electronic device. Right, now we can build the device we'll be working with, a bipolar junction transistor, which is just a diode connected back to back. PN junction diode connected back to back. Now you have this type of configuration. So this is a so here I have IN doped side. So for example, this is IN. I heavily doped. Intrinsic semiconductor, N doped, and here in between I have a very thin layer of a P doped and lightly doped, and here I have another N doped, and it also can be lightly doped. So this is called this is a bipolar junction. And the type of device, as I explained, how it works, is called a NPN, bipolar junction transistor. Now take this device and apply voltages in the device. So for example, if I apply here plus and here minus, I have a diode here in this region. So let me draw the band structure. So the band structure of this device is before applying the voltage. So if you look at the band structure, I have the N doped, so the N doped has charges, the electrons in the conduction band, and the Fermi level is here. The Fermi level is the same across the entire device. And here, as I have a P doped, the Fermi level is closer to the valence band, and I have this configuration. Sorry. And this is lightly doped, so I will put more electrons here. This is heavily doped, and fewer holes here. And here I have also electrons for the N doped side. This is the N doped, and this is P doped. And now I will connect these levels. So this is the band structure for the band configuration for this device if you don't apply any voltage. Now if you apply a voltage between these two sides, the P and the N doped, you can, if you apply this bias, you can shift the energy levels. So we will apply like in a forward bias, so that we will lower this barrier here. So if I lower that barrier, I can, so this is a low barrier, and the electrons can travel. Yeah, just in order to be consistent here, I just have to increase this barrier so that this will be consistent with this scale. So now when I apply this voltage, this bias, I change this barrier, I decrease the barrier. And now the electrons can go this way. So I have here plus and here minus. And on the other side, if I, so this will be like a diode configuration, but I also have this, the third semiconductor, the third extrinsic semiconductor. And now if I apply a voltage or bias between these two, between this and this, I get this configuration here. So I'm shifting this up here, shifting this down, and I'm shifting. And and then I'm taking this down here. So now I apply this voltage here, and the electrons, they can, because this is a very thin layer, it's not on scale here. Remember that this is very thin. The electrons can travel this way here. So they can jump from this n-doped side to this n-doped side. And this is called base. The p-doped side is called base. The n-doped side here is called emitter. And this side is called collector. So in this case, you establish a current here, and also the holes can move this way. So there are not many holes here, so this current will be very small. But the current from here to here, not from here to here, but the electrons, the number of electrons traveling from here, from this side, from the emitter to the collector, is very large. And by convention, of course, if the electrons are moving this way, the holes are moving this way, so this is the current. IB, let's call IB for I base. And if the electrons are moving this way from here to here, so the positive charges, by convention, are moving this way. So this is called IE. Let's call it IE for emitter. So you get a current this way. In this, you can only get this current, IE, if you apply a voltage, if there is a current in the base. So if there is no current in the base, there is no current from the emitter to the collector. So this device acts as a switch. So you can turn this current from the emitter to the collector on and off. So this is how your computer works, and turns on and off in the processing, in the CPU. Also, because this is heavily doped and this is lightly doped, and you have a very large number of charges moving from here to here, from the emitter to the collector, and a small number of charges moving from the base to the emitter. This works as an amplifier. Because you can amplify the current, so you can amplify IB. So IE, the current in the emitter, will be equal to this factor, this amplification factor, beta, times IB, where beta is larger, much larger than 1. So it works, it has two functions. So it works as a switch and also as a linear amplifier. And this is everything you need to know to work on the experiment. So I'll see you next time.